calculate the differential or the rate law. This is based on a table of initial conditions. So what you have is initial concentrations and initial rate. So you have concentration and rate. A simple reaction would have one reactant going on. Alright, so, and then trial. So trial 1, you're given or experimentally found that the concentration is 0.2 moles per liter, and the rate of change is 1.5 times 10 to the negative 5 moles per liter seconds. Trial 2, concentration is doubled. It doesn't have to be, but it's nice because it works out nicely that way. And you have the rate, which is 3 times 10 to the negative 5th. The formula, what you do is you plug in is rate 2 over rate 1 equals the concentration 1 over concentration 2 raised to the n. So what we're doing here is trying to find out what n is. And then you can write the rate law and find k. So the rate 2, you don't have to do it this way, but if you use the bigger number on top, it makes the numbers work out a little bit easier and nicer to use because you've got whole numbers and not fractions. So in this case, the rate 2, 3 times 10 to the negative 5th, divided by 1.5 times 10 to the negative 5th equals 0.4 over 0.2 raised to the n. The nice thing about this is you got a nice hold. So if you double the concentrations, it's really nice to do the labs. This is 2, 3 divided by 1.5 is 2, and the times 10 to the negative 5th cancel out, equals, that is 2 to the n. 1 power of n, 1 power of 2 will give you 2. N equals 1. So this is a first order reaction. If you were to write that, the rate is equal to K times the concentration of R to the first power, or just R. If you want to find out what the value of K is, you substitute the rate, times 10 to the negative 5th, equals K, 0.4 to the first. Solve for K, and that will give you the value of K, the constant, and then you can rewrite the law with the constant in there. So that's how you do these. And it's just a matter of working through and doing some math. Let's do another example. We have trial 1 and trial 2. The initial concentration of the reactant and the rate, 0.3, 0.6 moles per liter, 1.5 times 10 to the negative 8, 6.0 times 10 to the negative 8. So you take the bigger rate, or the bigger concentration on top, 6.0 times 10 to the negative 8, 1.5 times 10 to the negative 8, negative 8s will cancel, equals 0.6 over 0.3 to the n. That divided by that is 4, equals 2 to the n. 2 to the second power is 4, so it's a second order reaction. Again, you can go back rate equals K concentration of R to the second. Plug in the rate and the concentration, solve for K, and you can find out what the expression is. Another example, R rate 1 and 2, trial 1, trial 2, 0.05, 0.10 are your initial concentrations. The rate 1.5 times 10 to the negative 4, 1.5 times 10 to the negative 4, plug into the formula. The second one, the bigger number on top, so it's 1.5 times 10 to the negative 4, 1.5 times 10 to the negative 4 equals 0.10, 0.05 to the n. This is 1 equals 2 to the n. So n has to be 0. So this is a 0 order expression. And in this case, it's really easy to write it because it's to the 0 order. The rate is equal to 1.5 times 10 to the negative 4th. If the rate stays the same, you're changing the concentration. It's a good moment. It's going to be the same thing. Now, what happens if you have two different products or reactants? If you have two different reactants, your table expands. Reactant 1, reactant 2, and rate. So you need 3 trials, 0.25, 0.25, 0.50, 0.25, 0.50, 0.50. These are given to you where you find them out experimentally. 6.2 times 10 to the negative 7, 1.24 times 10 to the negative 6, 1.24 times 10 to the negative 6. What you do is you have to have only one thing varying at a time. So if you do 1 and 2, the R prime stays constant, so that's not affecting your thing. So if you want to find out what the R double prime is, you do that. So it's 1.24 times 10 to the negative 6 divided by 6.2 times 10 to the negative 7. We're doing experiment trial 1, trial 2, equals 0.50 divided by 0.25 to the n. That is 2 equals 2 to the n. N is first order n R double prime. Now you need to do an experiment where the R double prime stays constant and the R prime changes. So you double R prime, and you notice here the rate stays the same, but we're going to work it out anyway, so you know it's going to be 0 order in R prime. So we'll work it out anyway. 1.25 times 10 to the negative 6, 1.24 times 10 to the negative 6 equals 0.5 over 0.25 to the n. 1 equals to the n. N equals 0 in R prime. So the rate law would equal to K times the concentration of R prime to the 0 times the concentration of R double prime to the first. That is 1. So again, you plug in data from up here, either any of them, and it should come up with the same answer to solve for K. So you just got to pair up. The difficult part about this lesson is finding pairs where it doesn't affect your one thing holds constant and the other thing changes. That ends this lesson.